Hello, in this lesson, we will study linear and nonlinear systems of equations. We will learn how to solve systems using substitution, examine systems that contain nonlinear equations, and use graphs to understand how many solutions a system may have. Let's get started. In this lesson, we will focus on four primary objectives. First, we will learn how to use the method of substitution to solve systems of linear equations in two variables. Next, we will apply the same method to systems containing nonlinear equations. We will also explore a graphical approach for solving systems and determining the number of solutions. And finally, we will see how systems of equations can be used to model real-world situations. By the end of the lesson, you should feel comfortable solving a variety of systems and interpreting their solutions. A system of equations consists of two or more equations that are solved simultaneously. The goal is to find values that satisfy all equations in the system at the same time. There are two major types of systems we will study. A linear system contains only linear equations, and graphically, linear equations are represented by straight lines. A nonlinear system contains at least one nonlinear equation, such as a quadratic equation. For example, y equals 2x plus 3 and x plus y equals 7 form a linear system. One important idea to remember is that solutions correspond to the points where the graphs intersect. Any point that lies on both graphs simultaneously is a solution to the system. One of the most common techniques for solving systems is the method of substitution. The first step is to solve one equation for one variable. Next, substitute that expression into the other equation. This reduces the system into a single equation involving only one variable. Then solve that equation. After finding the value of one variable, substitute it back into one of the original equations to find the remaining variable. Finally, always check your answer in the original system. Checking solutions can catch arithmetic mistakes and confirms that the ordered pairs satisfy both equations. Let's solve the system. We have x plus y equals 4 and x minus y equals 2. We begin with the first equation and solve for y. Subtracting x from both sides gives y equals 4 minus x. Now substitute this expression into the second equation. Replacing y with 4 minus x, we obtain x minus 4 minus x is equal to 2. Distributing the negative sign and combining like terms gives us 2x minus 4 equals 2. Adding 4 to both sides yields 2x is equal to 6, and divided by 2 gives x is equal to 3. Now we are ready to find y. Substitute x is equal to 3 into y is equal to 4 minus x. This gives us y is equal to 1. Therefore, the solution is 3, 1. Whenever possible, verify the solution. Substituting x is equal to 3 and y is equal to 1 into the first equation gives 3 plus 1 is equal to 4, which is true. And substituting into the second equation gives 3 minus 1 is equal to 2, which is also true. Since both equations are satisfied, the ordered pair 3, 1 is the solution to the system. Substitution can also be used when a system contains a nonlinear equation. Consider the system. The second equation can easily be solved for y, giving y is equal to 2x plus 1. Substituting this expression into the first equation produces a quadratic equation, and after simplifying, we obtain 3x squared plus 2x minus 8 is equal to 0. Factoring gives us 3x minus 4 times x plus 2 is equal to 0. Therefore, x is equal to 4 over 3, or x is equal to negative 2. Next, substitute each value back into y is equal to 2x plus 1. So for x is equal to 4 over 3, we obtain y is equal to 11 over 3. And for x is equal to negative 2, we obtain y is equal to negative 3. Therefore, the system has two solutions, 4 over 3, 11 over 3, and negative 2, negative 3. Let's verify one of the solutions. Substituting 4 over 3 and 11 over 3 into equation 1 produces a true statement. Substituting the same point into equation 2 also produces a true statement. Since both equations are satisfied, the ordered pair is indeed a solution. The second solution can be verified in exactly the same way. Checking solutions is especially important when solving nonlinear systems because multiple solutions are often possible. Not every system has a solution. Consider the system shown here. First, solve linear equation for y. Y is equal to x plus 4. Substituting into the quadratic equation produces x squared plus x plus 1 is equal to 0. Using the quadratic formula yields a negative value under the square root. This means the discriminant is negative. Since the discriminant is negative, there are no real solutions for x. Because no real value of x exists, the original system has no real solution. Graphically, this means the graphs never intersect. The graphical method provides a visual way to understand systems of equation. When we graph both equations on the same coordinate plane, solutions correspond to intersection points. If the graph intersects once, the system has one solution. If the graphs intersect twice, the system has two solutions. If the graphs never intersect, the system has no solution. Although graphing may not always provide exact numerical answers, it helps us understand the behavior of a system and estimate the number of solutions. This makes graphing a valuable tool for checking algebraic work and visualizing relationships between equations. In closing, in this lesson, we learned how to solve both linear and nonlinear systems of equations using the method of substitution. We also saw how systems can have one solution, multiple solutions, or no solution at all, and how graphs help us visualize these possibilities. Understanding systems of equations is an important foundation for future topics in algebra, calculus, and many real-world applications. Thank you for watching, and I look forward to seeing you in the next lesson.